Welcome. It's nice to have you along with me as we finish this last section of Chapter 8. And then we'll be ready to review and get ready for the test. We're looking at 8.5 and 8.6, and actually we are only looking at 8.5. 8.6 is identifying special quadrilaterals. We are really doing that in class, so don't worry about looking at that as a separate section. Go ahead and cross that out in your notes. And we're just doing 8.5. 8.6 is applying all these things, and like I said, we're going to do that in class. So 8.5 is looking at the properties of trapezoids and kites. So here's our quadrilateral family, our parallelogram and rectangle, rhombus and square. We talked about that. And now we're looking at trapezoids, and in particular this isosceles trapezoid, and then also kites. So we're on this side of the family tree to finish up Chapter 8. So how can I use properties of trapezoids and kites? First of all, we need to know what are the properties of trapezoids and kites, and then how can we use them? Okay, what's a trapezoid? Well, remember, a trapezoid is one pair of parallel sides. So it's a quadrilateral that has one pair of parallel sides. And you'll remember that if it has two pairs of parallel sides, that is a parallelogram. But we are looking here at a trapezoid that has only one pair of parallel sides. So make sure and designate or notate these two sides clearly as parallel. That's the key point right there. As long as those two sides are parallel, then it doesn't really matter about anything else. This side could even be kind of tucked on the inside, doesn't matter. It is going to be a trapezoid as long as there's only one pair of parallel sides. And those two parallel sides we call bases. So you'll remember with a triangle, when this comes all the way up to the top here, and for an isosceles triangle, this is called the base, but in a trapezoid, it actually has two different bases on it. And so technically, each of these four angles are called base angles, and these other two sides are called legs. So the ones that are parallel are called bases, and the other two are called legs. And because these two bases are parallel with each other, let's extend, on your notes if you would, extend this one side here, and let's call that a transversal, or think of that as a transversal. So here's a line that is a third line that's crossing these other two lines. And let's look at these two angles here. And they are not on alternate sides of the transversal. They are on the same side of the transversal. And they're not exterior to those other two lines. They are both interior. So these two angles here are same side interior angles. And what is true about same side interior angles when the transversal is cutting across two lines that are parallel to each other? Well, those same side interior angles are supplementary. And what does that mean? It means that the sum of those two angles is 180 degrees. So these same side interior angles, angle A and B, the sum of these two is 180 degrees. And then same thing over here. The sum of these two is also 180 degrees. So we're not saying that these are congruent or across from here. Remember with a parallelogram that the opposites were congruent or things like that? We're not saying that. We're only saying that the same side interior angles are supplementary. And you will remember, though, where's my sheet, that for a parallelogram, that was true for any of the consecutive, here it is, any of the consecutive angles. in a parallelogram that these two are supplementary. These consecutive angles are supplementary, as well as these other two are supplementary, as well as this pair and also this pair. Okay, because you have two pairs of parallel sides. With a trapezoid, you only have one pair, so it's just the transversal that cuts across the two parallel sides, which are bases, called bases. That transversal creates these same side interior angles. Okay, so let's look at an example in the book. And they give us a coordinate plot here, and we have what looks like a trapezoid on the coordinate plot, and they want us to show and to prove that this is a trapezoid. So how do I do that? Well, what was the distinguishing factor of a trapezoid? It was that there was one pair of opposite sides that are parallel. So it looks to me, obviously, that these are not parallel, so it's probably these guys. I need to determine and prove whether or not these two sides are parallel with each other. So what do we know about parallel lines or parallel segments? Well, if they are parallel, they will have the same slope. Remember that? They will have the same slope. So how do I figure out the slope of this side? And then how do I figure out the slope of this side? And then let's compare them together. Well, remember that slope is, in basic terms, is rise over run, which, when we have the coordinates, is the change in the y, so y2 minus y1, over the change in the x. And so that's what they have done here, using these coordinates. And I would label this, maybe this is 0.1, this is 0.2, so this would be x1 and y1. Remember that? This is the x coordinate of 0.1 and the y coordinate of 0.1. We're over here. This is x2 and y2. This is the x coordinate of 0.2 and the y coordinate of 0.2. And then just plug those in to your equation down here, and that's what they have done over here. And the slope for the top one is 1/2. The slope for the bottom one is 2/4. But wait a second, I can reduce that down to 1/2, and so therefore, yes, these two segments have the same slope. Therefore, those two segments are parallel. And because they're parallel, therefore this is a trapezoid. So that's what you want to do here for this. I did not plot this for you. I only gave you the coordinates. You have to plot the coordinates and then figure out which two sides you think, did I mess this up? I didn't do. Which two sides that you think are parallel with each other, and then take the slope of each of those sides. I've given you the formula. Please make sure that you write the formula down on your sheet of paper, and then figure out the slope for each of those two sides. So go ahead and pause the video and do that now. You also have question number 2, and asking you which of these angles are supplementary angles, and explain your reasoning. So put this into words. Give me some sentences down here. Write. Let's do some Wicker from Avid. Let's practice our thinking and our writing. And so put this into words for me. Why you think which two particular pairs of angles are supplementary. Let's look now at a isosceles trapezoid. So it's a trapezoid that's a unique trapezoid. Isosceles, we're familiar with that, with a triangle. Remember that? An isosceles triangle has two sides that are congruent with each other. An isosceles trapezoid is a similar idea. Here's your trapezoid. I have two sides that are parallel with each other, but I also, my other two sides, remember, these are called my bases, and these legs happen to be congruent with each other. And we call that an isosceles trapezoid. That's helpful because an isosceles trapezoid has a number of unique characteristics to it. In an isosceles trapezoid, or let me say it this way, if a trapezoid is isosceles, then we're told here that each pair of base angles is congruent. So this pair of base angles are congruent with each other, and this top pair of base angles are congruent to each other. Also, if it is a trapezoid that's an isosceles trapezoid, then what are we saying here? Oh, no, I'm sorry. They're saying it backwards, right? So let's ignore this one for right now. So continue my statement that if it's a trapezoid and an isosceles trapezoid, then down here, then the diagonals of that trapezoid are congruent. So this entire red segment, is the same length as this entire red segment. And it does not say it here, but it is true, and go ahead and note it here, that this top left segment is congruent to this top right segment. So I have single tick marks there, and also this bottom left segment is congruent to the bottom right segment. So these pairs of segments are congruent to each other. Now, are we saying that these diagonals are bisecting each other? And no, we're not. We're not saying that, but we are saying that the diagonals are congruent and that they create congruent parts of that diagonal on top, and the bottom parts are also congruent. Okay, so if we're able to prove that it's a trapezoid that is isosceles, it tells us two things. One, that the pairs of base angles are congruent. It also tells us that the diagonals are congruent. Well, how do we prove that a trapezoid is an isosceles trapezoid? Well, one way, of course, is to measure to know the lengths of the legs, and that those are the same. Or, what this is saying, if one pair of the base angles are congruent, that is sufficient to know that this is a isosceles trapezoid. So we're kind of going backwards here, kind of the converse of that. So if I know that one pair of the base angles are congruent, then I know that the other pair, you could say, the other pair are also congruent with each other, and therefore this is a isosceles trapezoid. Okay, so let's look at example number 2 in your book. See if I can move this stuff around. Here's a quick example. This looks like the cornerstone. What do they call this? Keystone. There it is. This is the keystone. Look up in this diagram here, in an archway. You'll see this architectural feature often, and this is called the keystone. This is the key stone in this entire setup, and oftentimes, if they've done it correctly, that keystone is a trapezoid. And in fact, it's an isosceles trapezoid. So we're told here that these top and bottoms are parallel to each other. We're also told that these legs are congruent with each other. Therefore, this is an isosceles trapezoid. And we know that in an isosceles trapezoid, that the pair of base angles are congruent to each other. So they tell us this is 85. Therefore, we know that this other angle is also 85. And we also know that for any trapezoid, it doesn't matter what kind of trapezoid it is, any plain old trapezoid, that the same side interior angles are going to be supplementary with each other. So therefore, if this angle is 85 degrees up on top, then the angle down here is going to be 180 minus 85, which is 95. So this angle on the bottom right is 95, and because this is an isosceles trapezoid, therefore both pairs of base angles are congruent to each other. So if the right one's 95, then the left one is also going to be 95. How should I do this? I'll put this over here. Whoa, whoa, don't fall off. Okay, so there are no problems that you have to do here for a isosceles trapezoid, but you will need to know these characteristics in the future for quizzes and for the test. But I just did not have room to pack it in. All right, let's look at midsegments. Now we're looking at midsegments in a trapezoid. Hey, we've talked about midsegments before. Remember, midsegment goes midpoint to midpoint. Median, you'll remember, goes from vertex to midpoint. So that's a little bit different. But midsegment goes midpoint to midpoint. And so here's a midsegment of a trapezoid. Here's the midpoint of this leg of the trapezoid. And then here's the other midpoint of the other leg of the trapezoid. And this blue here is your midsegment. And remember that the midsegment was half of the third side when you have a triangle. Well, in a trapezoid, you have two bases, so you still have your half there, but instead of just the one base, the third side there, you also need to add the other base. So the length of this blue segment is 1/2 the sum of the two bases. So the length of the blue is 1/2 times the length of the red plus the length of the green. So we're basically finding the average of these two. So here's some examples. If this top base was 8 and the bottom base was 12, if you add those together, 8 plus 12 is 20. Divide 20 by 2, which is the same thing as multiplying times 1/2, and that gives you 10. Okay, and notice here that just like any midpoint, any average, that it is 2 units to go from 8 up to 10, and it's also 2 units to go from 10 up to 12. So sometimes what they're going to do is they're going to give you the length of the midsegment and the length of one side, and they're going to ask for the length of the third side. So how would you do that? Well, you could plug that into here and then create an equation and then solve for one of these if you wanted to. Or, so what I mean by that is this 10 would go over here. So it'd be 10 equals 1/2 times, and the 8 would be here for the length of AB. It'd be 8 plus, you could say like x. And then you solve this guy for x. Or what you could do is to say, hey, to go from one base to the midsegment is 2, and I know that this midsegment is the average of the two lengths of the bases. So if it's 2 to get to the midsegment, then I need to go 2 beyond that, and therefore the length of this other base is going to be 12. Here's another example. That if I have two bases at 2 and 8, add those together, it gets 10, divide that by 2, and I get 5. And let's say that they told you that one of the bases was 8, the other base was, the midsegment was 5. Okay, so it's 3 to go from the base up to the midsegment, and therefore, to find the other base, what I do is I go 3 beyond, and in this case I'm getting smaller, so 5 minus 3 gives me 2. Okay. Let me just show you example number 3 in the book. Here's example number 3, and what do we know about this thing? Well, I see here that I have two single arrows. So these two sides are parallel to each other. That's all I need to know that this guy is a trapezoid. And then I also know these two segments are congruent, so this must be the midpoint on this leg. And then these